Thank you very much. So welcome everybody to the first session of today. Welcome to calling functions. And you might imagine this is a pretty basic topic, which however I feel is fitting for Saturday morning. So grab a cup of coffee, relax, and join me for 16 minutes in calling functions. Allow me to start to introduce myself a little deeper. So my name is Klaus. I indeed do C++ trainings and do consulting in C++. And apparently this is not enough C++ for me. I'm also writing C++ in my free time. For instance, I'm the author of the Blaze C++ math library. And as Jens just mentioned, I'm also the one of the 4 organizers of the Munich C++ user group. However, let's go into the topic. Today, I really want to go through all the details in calling functions. So we will go through an entire sequence of steps that are done when you try to call a function. Now, I said all the details. Of course, I'm limited to 16 minutes. This makes this particularly challenging. And so, unfortunately, I cannot really go into all the steps. So I will talk about name lookup. Unfortunately, we will not talk about template argument deduction. I will talk about overload resolution, the access labels, function template specializations. I'll unfortunately skip virtual dispatch, and I will call about deleting functions. We will in this course talk about the basic mechanics. We will also talk about all these keywords, the terms that we use when we call functions. All right. This talk does a couple of things. So it focuses on the basic mechanics of calling functions. I also tried to point out the surprising details, the things where I realized that people in my classes are usually very surprised. And I'll also try to give you further references whenever necessary. However, it's just 60 minutes. So this talk will not show all possible examples, all possible cases. It will also mention every single detail, every possible combination of things. And I do not try to be bleeding edge. You will actually see C++20 syntax in, I think, a couple of places, but it's not about the latest standard. It's really about the basic mechanics to have at least one talk out there that can be used as a comprehensive learning material. So let's dive into what happens if you call a function. The very first step that we do is called name lookup. It's called name lookup, so the compiler looks for names, might find anything, functions, buttols, variables, types, etc. The compiler tries to find everything that has a given name and build something that we call an overload set. It might also find a couple of templates. Of course, we cannot call templates directly, we have to instantiate them, and these instantiations might be used to extend the overload set. Some templates, however, might not be directly callable might not work out. The instantiation might fail. Still, this might not necessarily be flagged as an error. This is what we call SFINAE. Just to mention it here, I unfortunately cannot go into detail into this. Now, when we have an overload set, including potentially template instantiations, then of course at some point we have to decide which function is the one that we truly call. This is the task of overload resolution. So the overload resolution boils things down to viable candidates and finally to a best match. Once we found the best match, then we should check the access labels, because it might be that from a certain call point, the function is not accessible. Then also, it could be that the selected function is resulting from a function template, which might mean that we might have to look for function template specializations. Or it could be perhaps a virtual function. In that case, we should determine the real function to call. Of course, this happens then at runtime. And last but not least, perhaps the function that we have selected is deleted explicitly, meaning by means of equal delete. This is also something we have to check. So this is exactly the stack of individual steps that we now deal with. Before we get started, one last very, very important remark, and I believe this is key to understanding a lot of the things that happen. This call stack, or this sequence of steps, is a strict one-way street. Once we have found a set of functions and then later find that none of them work, we'll never go back to a previous step. So if name lookup succeeds, it is a step that is done. And if we later detect any kind of error, it is a hard compilation error. No turning back to any previous step. All right. So let's dive into the individual steps. And of course, let's start with name lookup. As the name suggests, we are looking for anything with a given name. So in this little example, I start with first a function f that takes a double. I call this function 1. And I have a namespace n1 that contains a second function f. That one takes an int, and I call this function 2. Now in the main function, I first of all call f with a 1.0. And surprisingly, it will call function 1. We call this unqualified lookup. We just ask for calling the most reasonable function f. Which, however, means that if it would call f with a 42, perhaps surprisingly does not call function 2, but also calls function 1. Unqualified lookup looks from the call site in the according surrounding namespaces, which in this case is not namespace n1, but only the global namespace. I cannot see the function in the namespace n1, so the function 1 is the only option that I have at this point. So despite the fact that I have to convert the int to double, function 1 is called. It's the only function available. If I really want to call the function in the namespace n1, I have to say so by means of qualified lookup. So n1 : f triggers this qualified lookup. I now find the function f in the namespace n1. This qualified lookup will find anything that is visible within namespace n1 explicitly. Which means if I now imagine that there is no function f in the namespace n1, then this third call would suddenly result in a compilation error. There simply is no function f or anything called f in namespace n1, so this is now a hard compilation error, which is quite reasonable. We ask for n1, there is nothing. Let's assume that we get function f with an int back, so function 2 is back, but we also have a function g and h. Function g calls f with a 1.0, meaning a double value, with qualified lookup, whereas function h calls f with a 1.0 with unqualified lookup. If in the main function I call g, do qualified lookup, then this call to f in g will result in calling function 2. Interestingly, despite the fact that I have a double value, it will convert the double into an int and call function 2. The reason is that officially function 2 is hiding function 1. And exactly the same thing is happening if I call h. So whether I use qualified lookup or unqualified lookup, both will result into calling function 2. Function 2 is said to hide function 1. Even though there is kind of 2, the compiler stops after having found the function f in namespace n1. So this happens in the call to h, so the unqualified lookup. It will find function f here. It will not continue looking for any other function f because it's happy that it has found a function with the according name. So this just is not visible anymore. Function 2 hides function 1. And this is even true if function f takes an argument that is not really reasonable from the call side. So we pass double values in both cases. In the first case, of course, it's a compilation error because I'm asking for this f doesn't apply. However, it's also a compilation error if I call f unqualified from the function h. Again, the compiler only finds function 2. It does not see function 1, which now might be the one that I'm looking for. It only finds this f. And only later, in the overload resolution, we actually detect that this is not a function that I could call with a double. But as I said before, this entire sequence of steps is a one-way street. At this point, we only find this f, and if we later detect any kind of error, it is a hard error. We do not go back and try to look for any other function. All right, the same problem, or at least a similar problem, appears if I have a variable f in the namespace n1. Then both of these calls, again, are ill-formed. It's called name lookup. I look for anything that is called f. There could be types, there could be variables, But of course, they could also be functions. But if anything else but function is called f, this might result in some kind of name ambiguity, and the call would be ill-formed. So again, the variable 2 now hides, because it has the same name, the function 1. Let's assume that I call g. This time there's only function 1. Now, of course, for the sake of completeness, this will result in a compilation error. There is no function f in namespace n1. And if I call h, this now will call function 1 unqualified. There is no function f in the namespace n1. So if the compiler turns up empty in a certain scope, it continues into the next scope. And this is where it now finally finds function 1. Function 1 is finally called. Not from this, however, qualified lookup is very specific. Unqualified lookup is the thing that works in this situation. Now, let's assume that I get the function 2 back, but this time I do not explicitly call n1f, but :f, which is a shortcut for calling something in the global namespace. In this case, this function here will resolve to the global function. So this will call function 1 with qualified lookup. The second call, the call from h, calls 2 by means of unqualified lookup. So hopefully these examples give you some idea how function hiding works and the difference between qualified and unqualified lookup. Let's assume that we have a third function f, a function f that takes a double in namespace n1. However, it is defined after function g and h. Despite the fact that I now have a function f that takes a double, still g resolves to function 1, and h will still resolve to function 2. Function 3 is never considered. This is because it is defined after, no, even declared after the call site. So function 3 is not involved in this particular situation. It cannot be called. Let's make this a little more interesting. Let's add a struct s, and this s comes with another function f that takes an int. This is now my function 3. It also has a function g, which calls f with a 1.0. This call to f, assuming that I have an s and call g, will primarily, first of all, resolve to the third function, function 3. This is the first function that the compiler finds. It finds something in the current scope, the scope of the function call, and this is the only function that makes sense at this point. So again, I convert the 1.0 to an int, and function 3 is called. Now in this context, function 3 hides functions 2 and 1. Again, function 4 does not play a role in this context. If I get rid of function 3, then there's no f in s, which means the compiler continues looking in the next scope, which would be the namespace n1. Function 2 is found, and function 2 is ultimately called, again by converting a double into an int. And again, function 4 is not considered, but function 2 again hides function 1. And if I get rid of function 2, then last but not least, I would indeed call function 1, again by means of unqualified lookup, and again, function 4 is never considered. This explains something that I realize is pretty surprising for a lot of people, especially people that come from Java and C#. Let's assume that we have a base class with 2 virtual functions called f. The first one takes an int, the second one takes a double. And my functions 1 and 2 now. And this base class is derived from in this class, so class derived is a base and introduces a third function f. This one takes a double 2, and of course it overrides function 2. So I'm function 3. I create a derived object and I call f with an integer. And now, surprisingly, it does not call function 1. This will resolve to function 3, exactly because of the reasons that I explained before. In this case, I know the static type. Due to the static type, I know that this is the derived object. So I start looking in this scope. And the compiler does find a function f, function 3. However, it is satisfied at this point. It does not continue looking into the next scope, which would be the base class scope. It only picks function 3. And so this is the only function that later is a viable candidate, and so the function 3 is called. Function 1 is never visible. Function 3 hides function 1 and 2. And this indeed is very surprising to people from almost any other language, but this is exactly how it works in C++. So do remember that we have this hiding effect, and it is especially, let's say, scary in the context of derived classes. Now, there is one other mechanism that we can use to call functions. So let's assume that I have a function f double in the global namespace again, my function 1, that I have a function f that takes an int in namespace n1, that again I have a struct s in the namespace n1, but also a function f that takes an s. This is now my function 3. In the main function, I create an n1s and call f. From everything that I've said so far, function 3 would never be considered because it is declared after the struct s. However, still, in this context, function 3 is indeed called because it's the right function to be called. And this mechanism is called argument-dependent lookup. My argument is an n1 : s. This s is from the namespace n1. And in that case, the entire namespace n1 is considered, and I try to find a function that matches best for this s. And so function 3 is indeed selected, which is of course great, because only after I know s, I can define the function f that takes an s. This mechanism also works in this context. I now added a function template g that takes any kind of t. And this t is used to call a function f. If in the main function I call g with s, this little s here, then I instantiate the function template with capital S and of course would call f with an s. Also in this case, I would call function 3 based on argument-dependent lookup. And that also, of course, at the point where I implement or declare g, I have not seen the namespace n1 or the function that takes an s. Still it works thanks to argument-dependent lookup. If, however, I would introduce a fourth function, a function f that takes an s in the global namespace, then interestingly, this call here would result in an ambiguous function call. Argument-dependent lookup also considers the home namespace of the given argument, hence the name, argument-dependent lookup. But it also considers all the functions that are defined in the namespace that I would usually find. So the compiler sees function 4, but it also, due to our ADL, finds function 3, and both are equally well matched. There's no better function here, and so the compiler cannot decide which one is better. You have to disambiguate somehow, perhaps by means of qualified lookup. So remember that ADL only works for user-defined types. Only when I introduced s, my own type, ADL kicked in. For built-in types, which means ints, double, floats, etc., the regular rules apply. No ADL is used here. Now, pretty important distinction, only class types and user-defined type gets the benefit of ADL. This, however, also brings me to something that you should remember. So let's say that, again, we have namespace n1 with an s. This time I introduced a swap function that takes s. 2s, but I swapped, of course. In some function template g, I get two values of the same type, and I call swap on them. I call g with 2s. Of course, I would like to call function 1, but because I use qualified lookup at this point, std swap, std swap would be called. This is not exactly what I have in mind here, though. There is probably something special about swapping an s. I would like that function 1 is called. I should not explicitly qualify this call with std : but instead I should say using std swap and call swap unqualified. This using enables the compiler to choose STD swap, but else the unqualified code is enabling me to use ADL. So argument-dependent lookup only works on user types and only if you do not call a function qualified. So prefer unqualified name lookup to qualified name lookup simply because this enables ADL. And the core guideline C165 is using for customization points. Swap is usually one of the functions that we would like to call unqualified because it is one of these customization points. All right, then the last thing about name lookup that I would like to show you is something that we call two-phase lookup. In a global namespace, I again have my function 1, my function f that takes a double. I have the function g from before, but I also now introduce function 2 that takes an int. I have an s, I have the fs again, my function 3, which I first of all call indirectly by means of calling g. So this is the ADL lookup example. I call function 3 by means of argument-dependent lookup. However, if I now call this function template g with a 42, then this does not call function 2, as many people would expect. This now calls function 1. 42 is an int, a basic type, fundamental type. And a fundamental type is basically the basic rules, the fundamental rules are applied to this kind of type. This function has not been declared at the point where I call this function. And despite the fact that this is of course instantiated only down here, still the regular rules apply. So only function 1 is an option at this point. So only function 1 can be considered, may be considered, and so function 1 must be called. So no ADL, but the regular rules. All right, there's no question so far, so I simply continue with the next step, which would be argument-dependent, template argument deduction. Template argument deduction is a pretty interesting topic in itself, but seriously complex. And unfortunately, in the 60 minutes, I don't have time to really go through all the possibilities in template argument deduction. So I leave it to an expert. I would recommend Scott Meyer's talk about this topic from CPPCon 2014, C++ type deduction and why you care. This is actually a pretty amazing talk, despite the fact that it sounds like a very dry, very boring topic. Still, he made this a pretty entertaining talk. So really recommend it if you're interested in how this mechanism works. I mentioned before that when we instantiate some function templates, we might actually encounter compilation errors that still are not flagged as a compilation error. This mechanism is called SFINAE, also part of the step. And again, I do not have a lot of time to do this myself, but there is a 1-hour talk just on that topic given by Arthur Otwaya at CPPCon 2017, a subset of SFINAE. SFINAE is a pretty complex topic, but still I think Arthur managed to introduce this in a beginner-friendly way, so a really recommended talk. So I now assume that we have instantiated function templates as needed. We've extended our overload set, and we come to the next step, overload resolution. The task of the overload resolution is now to figure out which one function we truly call. And this step is split into 2 other smaller steps. First, we compile a list of what we call viable candidates. So we may have a lot of additional functions, but not all of them are actually reasonable. And so we strip down this overload set to viable functions. What is a viable function? Well, for instance, assuming that we have this call to f with a 42, then a viable function is of course a function that takes an int. This is what we call an exact or identity match. This works. Also, if we would take this by reference, this also would work. This is what we call a trivial conversion. We add a const. Standard conversions, functions that would be callable by means of standard conversions, also work. And so would functions that would require me to do some user-defined conversions. So a function that takes a widget, but a widget that can be constructed by means of an integer. Also viable. Functions that take several arguments but have to use default arguments, viable candidates. Functions that are constrained by C++20 concepts, but constrained such that the constraint matches, are viable candidates. And last but not least, functions that virtually take anything, take an ellipsis argument, this is also a viable candidate. A non-viable candidate would be a function that takes less parameters, like this f that takes no parameter. Of course, functions take more than one. Functions that take arguments that I cannot convert the int into, for instance, a string. And of course, also functions that are constrained such that the constraint would be violated, like this function that only takes floating point values. So I discard all the functions, all the candidates that are non-viable, and I'm left with a set of viable candidates. And now I have to select the best match from this list of viable candidates. So I have to determine which one is the best match. That's the real task, the complex part of overload resolution. And this really is a very, very complex matter in itself. So I can only be brief about this. And to give you an idea how this works, I will just use a single argument. At the end, I try to give you an idea how this works for multiple arguments, but let's stick to a single one first. I have a lot of possibilities. First, indeed, we could have something that is called an exact or identity match. This would be perfect. This would definitely work. It would also work if I just have to add something like a const, a trivial conversion. The compiler considers these two to be rank 1 functions. Possibly the best thing that could happen. Then, of course, the next best thing is something that is a conversion, but a special one, a promotion. And a promotion can be mixed with a trivial conversion also. This is what the compiler considers to be rank 2. I'll explain in a second what a promotion truly is. Then the next level would be a standard conversion, like an int to double. You've seen this before, or perhaps a standard conversion followed by a trivial conversion. This is what the compiler considers rank 3. And then there is more possibilities. Perhaps there's user-defined conversions. And of course, user-defined conversions and trivial conversions, or perhaps user-defined conversions and standard conversions. Officially, this doesn't have a rank, but we might imagine that this is like a rank 4. And an ellipsis argument would be the final step, like the rank 5, the worst thing that could possibly happen, least priority. So let's take a look at a couple of examples. Let's say that in my function, I have an integer, and I call a function f with an int. This is my two viable functions. I have a function f that takes an int ref, and I have a double. Function 1 is considered to be a rank 1 function, an identity match. I have an int, it takes an int, perfect. In order to call function 2, I would have to convert from an int to double. This is deemed to be a standard conversion. Therefore, in this particular case, function 1 wins, which is obvious, hopefully. But now I add a third function, a function f that takes a constant int ref. Function 1 still is an identity match, function 2 still is a standard conversion, but function 3 now also is identified as a rank 1 function. So at this point, I would have a tie between function 1 and 3. Luckily, there is a tiebreaker, because intuitively, we actually realize that function 1 is probably better suited. I have a mutable int, I should call function 1. The standard defines a couple of tiebreakers. And since I believe CPP reference to be a little easier to understand, I now go to overload resolution in CPP reference, and we scroll down quite a bit. It's a pretty lengthy article to this particular point here. So ranking of implicit conversion sequences and node 3. A standard conversion sequence S1 is better than a standard conversion sequence S2 if, now we scroll down a little more, if both S1 and S2 are binding to reference parameter, only different in top-level CV qualification. And S1's type is less CV qualified than S2's. And interestingly, it gives exactly the same example as we've just seen. So the example where I have a mutable int, this function and that function, and the standard says explicitly, in this particular case, function 1 is preferred. They're both rank 1, but due to this tiebreaker, I have a preference. So function 1 is called. If, however, the compiler cannot really find the best match because two functions are basically equally well matched, then the call is said to be ambiguous. So I have an int again, I call f, but this time the two functions that I have take float and double. Both functions are ranked 3. Both are considered standard conversions, although of course different standard conversions, but still rank 3. There is no tiebreaker, there is no special rule, so this is an ambiguous function call. The compiler will not prefer one of these two functions. You have to be explicit. You might have to convert the integer into float or double explicitly in order to say which function you truly want to call. There is a special, pretty interesting ambiguity between a non-template and a template. So let's assume that I have a function f that takes an int, and that I have a function template which is constrained to integral values only. If I pass an integer, then in the second step that I mentioned before, template argument deduction, the second function is instantiated to take an int. So essentially, this function template results in this function. Now, these two are very, very, very similar, if not even equal. And a compiler would consider both of them identity matches, so both are rank 1. Also in this situation, we need a tiebreaker. And also this is something we find if you scroll down to the best viable function section. f1 is determined to be a better function than f2 if implicit conversions for all arguments of f1 are not worse than the implicit conversions for all arguments of f2, and f1 is a non-template function, while f2 is a template function, a template specialization. So the non-template is indeed preferred. In our example, the second function results from a function template, the first one does not, and so this calls function 1, which is something to keep in mind indeed. This situation of course, only applies to identity matches. Templates tend to be instantiated as identity matches, and so as soon as this is not an identity match anymore, the template would be preferred. But in this situation, it's the non-template. So, the second level, the second rank, is called promotions. And there's only a very, very small set of conversions that a compiler considers to be special. So, for instance, an unsigned short can be converted to an unsigned int or int, depending on the platform, or a short can be converted to an int, a char can be converted to an int, or unsigned int, depending on the platform, and a bool can be converted to an int. This is the so-called integral conversions, and this is all of them. There's nothing else that is considered special. And there's only one floating point promotion. Float can be converted to double. If I would convert a float to long double, for instance, it would not be promotion. Yes, sure, the float also is extended, it gets bigger, but still it is not considered to be promotion, but a standard conversion. So, two examples here. If I have two functions, one takes an int, one takes a double, but I have a short that I pass to f, then of course this calls function 1 now. Function 1 is considered to be an integral promotion, rank 2. Function 2 is only a standard conversion. So I call function 1 because of a lower rank. It is a conversion, but a special one. If, however, I use a float down here, so 4.2f, I pass this to the function, then suddenly the first function would be a standard conversion, and the second one would be a promotion. So the second one suddenly is better fit for the given argument. Function 2 is called. If it is not a promotion, then it is like float to long double or any other kind of integral conversion like int to unsigned int. It's just a standard conversion. There's of course integral conversions. Floating point conversions. Then I can convert integral numbers to floating point numbers and floating point numbers to integral numbers. There is special kinds of pointer conversions, of course derived to base conversions, and any pointer can be converted to void pointer. And I can convert booleans to boolean in many ways. There's a lot of possibilities, but it is only considered rank 3. So, for instance, I have an unsigned int, I pass it to f, and it is converted into a double. So, of course, this calls function 1 by means of a standard conversion. If I have a function f that takes an int, it also is considered a standard conversion, and I call function 1, this function 1 now. If, however, I now have these two possibilities, the function that takes a double and the function that takes an int, and I pass an unsigned int, then maybe people tend to assume that this calls function 2, which it doesn't. This results in an ambiguous function call. Both functions, the first and the second one, are considered to be standard conversions. Both have rank 3, and there is no tiebreaker or special rule that would make function 2 a better candidate. So indeed, in this situation, there is an ambiguous function call. You have to be specific again which function you want to call. Now, one example of about class hierarchies. Let's assume we have a class A, struct A, which is used as a base class for B, and B in turn is used as a base class for C. I have two functions f, one takes an A pointer, one takes a B pointer, but I pass a pointer to a C. And in this case, indeed, function 1 would be pointer conversion, rank 3, and function 2 would be a pointer conversion also, rank 3. If there would be no tiebreaker, they would be equally well matched. But of course, function 2 is better, and there is a special tiebreaker. This would call function 2, because we intuitively would also consider this as a better conversion. It's the closest pointer, more fitting for a C pointer. If it's not a standard conversion either, then it can only be a user-defined conversion. And user-defined conversions are provided by means of constructors and conversion operators. So if a class, or struct of course also, has constructors that take some arguments and that are not explicit, and if the class would introduce conversion operators that are also not explicitly set to explicit, then these operations can be used for conversions. For instance, in this call, I now have a struct widget that allows me to create it by means of an int. Again, I have two f. One function takes a long, one function takes a widget. I'm passing an int, however. Both functions are viable. The second one is viable because I could convert the int into a widget by means of this constructor, and so I could indeed call this the function, but function 1 is considered to be a standard conversion, and function 2 is only a user-defined conversion. So in this example, function 1 wins. But as soon, of course, as function 1 is not there anymore, function 2 is called. So this is something that we also find in this subsection, ranking of implicit conversion sequences. A standard conversion sequence is always better than a user-defined conversion sequence or an ellipsis conversion sequence. So user-defined is indeed only considered something like rank 4. It's not officially a rank 4. Rank 4 doesn't exist, but this is what you can consider to be. So let's consider a couple of user-defined conversions. I have a struct widget, has two constructors. One takes an int, one takes a double. I constructor 1 and 2. I have a function f that takes a widget, and I pass an integer to this function f. Then yes, this function f is called by means of calling the first constructor. The first constructor is considered to be a user-defined conversion. Just one user-defined conversion, then I have a widget. The second constructor is also viable, but it requires me to do user-defined conversion from int to widget, and also the int has to be converted from int to double, which is an additional standard conversion. This is more expensive. It is considered less suited, so function 1 is selected. If I have a short and pass this to function f, also function 1 is called. This time because I have a user-defined conversion plus a promotion, whereas the second function still is a user-defined conversion plus a standard conversion. So function 1 again is a little better because the sequence of conversions is cheaper in a sense that it has a lower rank. So again, calls function 1, which is better matched. So also this is described here. You have to scroll down to note 4. A user-defined conversion sequence U1 is better than a user-defined conversion sequence U2 if they call the same constructor / user-defined conversion function or initialize the same class with aggregate initialization. And in either case, the second standard conversion sequence in U1 is better than the second standard conversion sequence in U2. So user-defined conversions have the same rank, and then it is decided based on what else do I have to do. So this is not all the details, as I said before, but it should give you a pretty good idea how it works with a single parameter. Now, how does the compiler decide on the best match if you have multiple parameters? Well, essentially, it is just applying the same rules to every single argument. If you have two functions to choose from, then only if one function is considered better for at least one argument and is equally good for all the other arguments, then the function is the best match. This function would be selected. Else the function would be ambiguous. So allow me to give you an example again. Let's assume that I have two functions f. The first takes 3 integers, the second takes an int and 2 doubles. And I totally agree, this is a little contrived now, but it should really give you an idea how this is evaluated. So the first argument is an int. In both cases, this function takes an int. So for both functions, I would rate the first argument as a rank 1. The second argument is a short. For the first function, this would actually be a rank 2, meaning a promotion, whereas it would only be a conversion, a standard conversion for the second function, which is a rank 3. The third argument is an unsigned int, which you said before would be a standard conversion for the first, but also for the second function. In total, function 1 is a little better. It is equal in the first and third argument, but it is better in the second argument. And so in this case, function 1 is called, it's considered to be the best match. If I change the arguments a little bit, if I pass float as the third argument, then again, the first two would be considered rank 1. The second argument would be rank 2 and rank 3 respectively. But now, for the first function, the third argument would be a conversion, standard conversion, whereas for the second function it would be promotion. Now there's no obvious winner anymore. And it doesn't matter how many things are validated as better. As soon as there's one thing that contradicts one argument where the first function and one argument with the other function is better, it is already an ambiguous function call. Again, you have to make explicit which of these two functions you would call. But of course, I would generally stay away from this kind of situation. So, prevent complex overloading situations that may result in surprises during overload resolution. It's definitely best to implement things as obvious as possible. And I would also forward you to the core guideline C163, overload only for operations that are roughly equivalent. So if they're both called f, they should basically do similar things. It should not be weird to decide which one is indeed better matched. All right. So I see a couple of questions. The first question actually applies to the name lookup. So will ADL apply for type defs? Any name that you define. So a type def or as a type alias would be a name, would introduce a name. This name might be found, might actually interfere with your calling. And the second question, can you please repeat what makes the two-phase lookup special? Example looked rather similar to the one that was shown before ADL. Allow me to go back to the special case, which is this example. No. So I have to go back to exactly the right slide. Let me figure. Yeah, so two-phase lookup. The special thing about this scenario was that the function template is instantiated here inside main. And at this point, of course, everything has been seen already, function 1 and 2. Still, for fundamental types, the regular rules apply, which means function 2 is not selected. I perhaps highlight it specifically because some compilers in the past actually did this wrong. They would have called function 2, although strictly speaking, it would have been forbidden. With new compilers, the modern versions or the modern implementations, you would have no problem at all. So it will always work, it will do the right thing, but you should, of course, have an idea why it does the right thing. Okay, so I hope this answers these two questions, which means we can move on to the next step. So we've dealt with overload resolution, which is one of the most complex steps indeed, and we go now on to access labels. You might now yawn and say, oh my, this is a simple thing. This is just something obvious. Perhaps not. Also here, I find a lot of misconceptions with my students because it is perhaps not entirely intuitive. So let's consider this example. I have a class object with two functions f. The first function f is defined in the public section of the class. I call it function 1, it just takes an int. And the function f that takes a double is defined in the private section, function 2. I now create an object somewhere, some call site, and I call obj.f with a 1.0. At least 50% of people usually predict that this would call function 1 because it's public. It's the only public function in this scenario. It does not. This results in a compilation error. Function 2 is selected, but then, of course, the compiler realizes that this function is declared private and cannot be called. So this results in a so-called access violation. The reason is that the steps are really performed in the order I've explained before. First, I figure out if there's any function called f. And indeed, the compiler in the name lookup step finds two functions called f. Then, of course, there's no templates involved, so we go to overload resolution. The compiler decides that function 2 is the best match in this scenario. The argument is a 1.0. Function 2 expects a double. This is an identity match, rank 1, function 2 selected. Only afterwards, the compiler checks this access level and finds that this function is private. So I just said what it really is, and also the headline shows it. It's an access label. This is not a visibility label. The private section of a class is not invisible. It's not like nobody can see it. Everything inside a class is visible. I just cannot access it. And so it does matter what you do in the private section and also, of course, in the protected section of a class, because it might interfere with your call resolution. Yeah, any other name or any overload in the other section might interfere. And so please do not consider a class or any object as something made of stone, where there's only a couple of windows and doors where you can reach through. No, please consider this like a class object. Everything is made of class. You can see through the entire thing. You just cannot access things. And this is one of the reasons why there will be a new keyword in C++20, which is class. So you will be able to express very clearly what this truly is. It's a class object. And of course, now, don't take my word for it. There is no keyword in C++20 that is called class. I just think this is a tremendous, a very nice way to remember what it truly is. Yeah, so no new keyword, don't worry. Still, nice way to remember it. All right. So remember that everything inside a class is visible. Public, protected, and private are merely access labels. And with this, we go to the next step. Okay, let me answer the question at the end, since I've only 10 minutes left officially. Let me quickly go into function template specialization. This is something that also is pretty complex in itself. But let me make the point of why function template specializations might not be the thing that you're looking for. I have three functions now. First of all, I have a function template 1 that takes a t. Then I specialize this function template for char pointers. And then I introduce a third function, again a function template that takes a t pointer. In the main function, I actually initialize a char pointer something, and I call f. No, this will not call the second function, the specialization. This will resolve to function 3. Function template specializations are only considered after some function-based template has already been considered. So initially, the compiler only chooses between 1 and 3. And of course, in this context, function 3 is better matched. Since function 2, the specialization, belongs to the function template 1, it is not considered afterwards. So function template 3 is called, it's not function 2. However, this changes if I reverse the order. If suddenly this function template specialization is defined last, it is actually a specialization of the second function template. So function 2 now suddenly belongs to function 3. And now with the same call, suddenly I call function 2. That function template 3 is selected first. Then I actually try to find any kind of specialization. The compiler now considers the specialization 2, and indeed it's a better match, it is called. So function template specialization is different from overloading. An overload set is considered in the overload resolution phase, but function template specialization happens later. This resolution is delayed, and so perhaps this is indeed a little special. And it probably is also special because it is pretty tricky. If I, for instance, would just define this differently, if I would, for instance, make this a function template specialization that explicitly mentions char pointer, then because of that, suddenly it is a specialization of function template 1 again, and again function 3 would be called. So here the one in the middle. So function template specialization is indeed tricky. Prefer function overloading to function template specialization. And if you do it, you really should know what you're doing. This was a very, very short intro to that. There is a brilliant talk about C+ function templates by Walter Brown. I recommend the C++ on C version. It's close to 1.5 hours, so 120 approximately. It explains a lot of details. Very technical, but a very, very nice coverage of all these details. Which now leaves us with 2 points only: virtual dispatch, which however I'm going to skip, simply because this might be the one that is obvious how it works. And also Stefan has already covered this topic pretty well. So I refer you to Core C++ 4 of N, something that you find at YouTube. This is where Stefan explains in detail how virtual functions work. The virtual dispatch in general, what changes you have to experience in classes, so you will experience in classes when you introduce virtual functions, etc. Really well documented. Which only leaves us with the last step, deleting functions. Which, interestingly, is not what many people consider to be. So I have 2 functions f again. The first one takes an integer, the second one takes a double, and the second one is deleted explicitly. In the main function, I call function f with a 42, and it's called function 1, of course. If I, however, call function f with a 1.0, this will not call function 1, but it will result in a compilation error that tells you that function 2 has been explicitly deleted. Equal delete does not mean that the function is gone. Equal delete is basically similar to defining a function without giving it a function body. So you basically say, here is function 2, but actually you cannot call it. I explicitly prohibit you to call it. And so if you try to call it, this will result in a compilation error. So it reads like it's gone, it's deleted, but consider it more like an equal disable. You explicitly disable this function. And this may be pretty interesting. Okay, got it first. Equal delete doesn't delete a function, but declares it as uncallable. Any attempt to call a function will result in a compilation error. This has pretty interesting consequences in classes. Because, for instance, we could delete our move constructor. So, right, in the main function, I first of all create a default widget, W1, and then I try to move W1 into W2. This will not call the copy constructor instead, but this will result in a compilation error that tells you that move has been prohibited, has been explicitly deleted. If you really want to get rid of move, you should not declare it at all. Then, and only then, the copy constructor can be used as a fallback. Which is indeed a very interesting twist in the rule of 5 that also Nikolai Yasutis on day 1 has already mentioned. The rule of 5 tells us that we should either define all of the functions or, actually this is a different guidelines, 20, we should not define any of them. But if you really want to delete, get rid of the move operations, then you should not declare them. You should probably fall back to the rule of 3. They should not appear in your class at all. Which is just something, again, to remember, one of the twists that equal delete brings you. All right, and with it, I have covered the entire call stack, or the entire sequence of steps when calling a function. So we have covered name lookup, overload resolution, unfortunately I skipped template argument deduction. We've talked about access labels, function template specialization, and deleting functions. And of course, this was only a 60-minute kind of superficial walkthrough, but still I hope that this helps to better understand how compilers actually resolve function calls. With this, thank you very much for getting up early on Saturday, and I will try to answer a couple of more questions. So Dennis asks, can C++ 20 modules change the explained rules for access labels if only the public function f is exported? If you indeed call a function from a point where you cannot see the rest, this may make a difference. If you only export a specific function, then yes. Inside the class, however, of course, it is different. Inside the class, you will always have the behavior that I explained before. So explicitly exporting, yes, but as soon as it's visible, you will fall back to the thing that you've seen, the things that I explained before. Okay, what's the reason that access labels are checked after overload resolution, not before it? So it is indeed checked after the overload resolution because Björn Strustrup in the very beginning was actually very, very concerned that else it might be confusing. And I know this is perhaps now surprising that because it might now be confusing. But what he wanted to prevent is that calls to the same function suddenly have different meaning. So if I call a function from within the class, it should result in the same effect as I call it from outside the class. So the private keyword or also protected keyword should not change the way function resolution works. And this is why it is called after. Else I would call the public function in one case and a private function in the other case. This might be surprising also in a different way. All right, and last question. Do the same rules apply for function pointers, i.e. the resolution of void? So some example follows the same steps as for calling foo with an int directly? Absolutely. However, it does not probably follow the same rules as you might now consider it. Assigning to the function pointer follows the same rules. So if you select a function somehow and assign this to the function pointer, the compiler has to figure out which function you assigned to this function pointer. But as soon as you have assigned to the function pointer, the decision which function you're pointing to has already been made. So if you now pass the int, it will always call a function that has been bound to this pointer. So yes, initially with the assignment, it definitely follows the rules, whatever is visible right now, etc., etc. But calling the function is a straightforward process of just calling the thing that you've already selected. Okay, one more question, if I may. Isn't leaving such fallback to copy construct available going to make the code less expressive? We expect that using std_move should not make a copy. Well, that is, of course, now starting to be philosophical. This is the rules that we have today. Of course, we could argue that it would be much nicer if the rules would be different, but this is just what we have to deal with today. So perhaps you're right, perhaps it's better, it would be better, but this is just the way it is. So unfortunately, I cannot really tell you different things here. All right, indeed, I hope this was helpful to perhaps clarify a couple of points where we never were quite sure. Thank you very much again for getting up on Saturday morning, of course, and enjoy the rest of the conference. Thank you.